Hello, and welcome to Discrete Math site. Today, we're going to see part 2 of mathematical induction. I will start by reminding you of the principle of mathematical induction. So you need to show for any n greater or equal than 1, Pn is true. Then you prove two things. The basis step, P1 is true, and the inductive step, Pn implies Pn plus 1 is true. Once you prove this, then what happens is P1 is true, and P1 implies P2 is true, then P2 must be true. You take P2 here, so P2 is true, and P2 implies P3 is true, then P3 is true. You take this one and put it here, P3 is true, and P3 implies P4 is true, P4 is true, and so on and so forth. We, in part 1, we showed all these equalities, and we used some technique that in some of the upcoming examples can't be used anymore. But before, if you're asked to find and prove a formula for something like that, if you don't understand what this means, you can't really do it. You really need to understand what this means. So what you need to do, you need to expand this and take your time. You put I equal 1, you put I equals 2, you put I up to I equals n. So Pn is, you see when I is 1, that's 1 times 2. When I is 2, 2 times 3, 3 times 4. Last term would be when I is equal to n times n plus 1. So we need to find a formula for this. So what you do is you take one term, you take 2 terms, 3 terms, and see if you are getting some kind of formula, some kind of pattern that would help you find the formula. So we're going to start with 1. 1, you have one term, which is 1 over 1 times 2 is 1/2. And I'm going to leave it as a fraction here. I'm not going to turn it into a decimal number. Now, when you have two numbers now, see, so this one here is 1/2. This one here is 1/2. So you put it here, plus you added this to it, 1/6. You get 4 over 6, which is 2/3. Now you have three terms. So these two terms already 2/3. So you replace them with 2/3, and then you add this term to it, which is 1 over 12, and then you get 3 over 4. Now, if you take 4 terms, you see now I'm going to say these 4 terms, you have these 3, which are these 3, and I know those are 3 over 4. So I put the 3 over 4, and then I added this term. You add this, you get 4 over 5. Now, I'm noticing that 4 over 5, and I see here, so 4 over 5, 4 times 5. This 3 over 4, this term here, 3 times 4, that's interesting. 2 over 3, that's 2 times 3, that's interesting. So which means whenever I'm ending up here, I'm getting this 2 over 3, 2 times 3 is 2 over 3. If I do one more here, it's going to be 5 times 6, that 6. So I'm thinking that if I stop at n, I would end up having n over n plus 1. So that needs to be now proven. So the basis step is already done because we did it for n equal 1, 2, 3, 4, etc. to find the formula. Now you need to do the inductive step. So you suppose this is equal to this, and you prove it for n plus 1. That's Pn, and that's Pn plus 1. So you repeat this, and then you replace n by n plus 1, n plus 1, n plus 2. So you're adding one term. To this has to be equal to n plus 1 over n plus 2. So we need to prove this. Now, if you watch here, the left-hand side is composed of two things, this here and this here. So it's composed of this, which is this, and that's what we were seeing earlier in the example up there, which is this one here, plus this. So I take this n over n plus 1, I put it here, see that's the one here. And then this one here, that's the technique we used for all the previous examples. So now all we have to do is to add these numbers, add these fractions here and see what we can get. So we did here, we need to have a common denominator. We multiply this by n plus 2 over n plus 2, and then we add this together, get n squared plus 2n plus 1, and then you will see n plus 1 squared, and then you simplify this with this, and you get n plus 1 over n plus 2, which is the right-hand side. So that's done. Now let's see some different examples now. Here's one example. I need to show that 2 to the power n is less than factorial n for all values of n greater or equal than 4. Now here the mathematical induction doesn't start with n equal 1, because when n equal 1 or 2 or 3, this is not satisfied. When n is 1, this is 2, this is 1, that's not smaller than 1. When n is 2, this is 4, and this one is 2, and 4 is not less than 2. When n is 3, this is 8, and that's 6, and 8 is not less than 6. Now, it's when n is 4 that starts to work now for us. So the basic step is when n is equal to 4. So when n is equal to 4, the left-hand side is 2 to the power 4 is 16, and the right-hand side is factorial 4 is 24, and 16 is less than 24, so that works for 4. Now, the inductive step, obviously n has to stay greater or equal than 4. You suppose 2 to the power n is less than factorial n. You prove 2 to the power n plus 1 is less than n plus 1 factorial. So here you see we don't have that technique that we used in the past. So, and there is no such a standard way of solving problems like that. You just have to think of ways to do that. But whatever you do, you really need to use this. This must be used. So if I take this, I know it's true now, and I multiply both sides by 2, I get here 2 to the power n plus 1 less than 2 factorial n, and 2 is less than n plus 1. Then I can put this less than n plus 1 factorial n, and that gives me 2 to the power n plus 1 less than n plus 1 factorial, and that's what I was trying to prove. Now we need to prove that 3 divides n cubed plus 2n. And sometimes you see languages like n cubed plus 2n is divisible by 3, or is a multiple of 3, or 3 divides this is all mean the same thing. So basis step, n is 1, 1 cubed plus 2 times 1 is 2, that's 3, and 3 is divisible by 3. So now you suppose n cubed plus 2n is divisible by 3, and you need to prove this. So we replaced n by n plus 1, see? N plus 1 cubed, n plus 1 is divisible by 3. No matter what you do, you really need to keep in mind that this needs to be used sometime, somewhere, okay? So in this example, I'm going to take this and expand it. I will get n cubed, 3n squared, 3n plus 1 plus 2n plus 2. Now, do not add the 2n to the 3n here, because you get into a issue here you can't really find it that easy to solve. What I need to do is I'm keeping in mind this. then I have to have this term, keep it alone, separate. So I took the 2n from here. I took the 2n from here. I can't get this to work. Yeah, it's right here. I took this here and put it beside the n cubed. Then I'm left with 3n squared, 3n, and 1 plus 2 is 3. So I get 3 outside, n squared plus n plus 1. And now you see that this is here is divisible by 3 right there. And this one here is obviously divisible by 3. Then the whole thing would be divisible by 3, and that conclude the proof. The last example today is we want to prove that 10n squared is less than 2 to the power n for n greater or equal than 10. Why greater or equal than 10? Because if you try 1, 2, 3 up to 9, this one will be larger than this one, bigger than this one. It's only when n becomes 10 or more that this becomes less than that. So the mathematical induction here, the mathematical induction here has to start with 10. So the basis step is n equals 10. You replace 10 here. 10 squared is 100 times 10 is 1000. And 2 to the power 10 in the 1024. And 1000 is less than 1024. Now this one is a little bit more complicated than the previous example. Now again, keep in mind n is greater or equal than 10. Suppose 10n squared less than 2 to the power n, which is what we are trying to prove here. And we need to prove 10 replacing n by n plus 1, n plus 1 squared less than 2 to the power n plus 1. So now if I take this, which I know it's true, and multiply both sides by 2. By 2. So that's what I did here. Now, this here is 2 to the power n plus 1. So now I know that this compared to this is less than this. So if we can prove that this term here less than this term, then we're done. Because if I prove this less than this, and I know that this less than 2 to the power n plus 1, then this becomes less than 2 to the power n plus 1. So I need to see how we can prove this here. So I need to prove this, and I know this is equivalent to this. I simplify both sides by 10. Okay. So showing this is the same as showing this. Expand, showing this is the same as showing this. So now I take the 2n to the other side. I take these two terms to the other side. 2n squared minus n squared, I get n squared minus 2n greater or equal than 1. So this is equivalent to this. And this one is equivalent to this. I put n outside, n minus 2. Is this true? The answer is yes, because n is greater or equal than 10. So this will be greater or equal than 8, greater than 10. So obviously this is greater or equal than 1. So this is true. This means this is true. This is true. This is true. This is true. And then if I go back to the here, then I have this. Where is this my cursor now? Okay, then I have this is less or equal than this. I just showed that. And this one is less than this. Then this becomes less or less than 2 to the power n plus 1, which is this one. And that is the end of mathematical induction part 2. More videos to come. Thank you.